Today I'm going to be repairing a NASCOM 1 computer from the 1970s. The date codes on this board suggest that it was kitted in around 1978. There are three separate parts to this computer. Firstly, the power supply. So this is an original NASCOM 3 amp power supply. When I acquired it, there were signs of leakage around the smoothing capacitors, which I've replaced, and one of the regulators also had gone short circuit. I've also replaced that. This power supply provides 3 amps at 5 volts, and it also supplies plus or minus 12 volts at 1 amp and minus 5 volts at 1 amp. This one's in a nice metal chassis with some cardboard that I made to stop myself from electrocuting myself. Seemed like a good thing to do. Next, the keyboard. So this one has been modified to add some extra keys which make it a bit more like a NASCOM 2 keyboard. Unfortunately, the reset switch, which should be here, has broken off. It should look like this. This is a different type of switch than the keyboard switches, and it's prone to just pop off. However, the contacts are still here and it will still function, so that's okay. If we look at the back side, you can see the wiring is a bit, well, not terribly tidy, but the soldering looks good. There's a couple of scrapes here, but the tracks are not damaged. I've tested this keyboard on another machine and I know that it works fine, so I don't see any particular reason to mess around with this wiring. The keyboard's scanned under software control. There's a counter here which is clocked under software control from the NASCOM, and it selects the rows and columns of the matrix keyboard. So one failure mode is that the keyboard totally fails to operate, and it can be quite difficult to debug because you can't really do anything unless you have a NASCOM that's running correctly in order to poll it. But typically one of the reasons that the keyboard fails in this way is it may have been connected backwards, in which case a lot of the logic will have been stressed and some of the chips might have died. You can go around and look at the logic levels on the keyboard and maybe find a bad chip. The other thing which happens on some machines is that you'll find that most of the keys work but some of them don't, and if you look at the keys that don't work, you'll normally find that they correspond to a particular row on the keyboard, and each of these rows goes through one of these CA3080 chips and CA3086 chips here, and all that these actually are is NPN array, 4 transistors in a package. You can buy replacements of these, but it's just as easy to use a little header and wire up 4 BC108s or something like that. So if you have a bad row, it's probably one of these transistors, or it might be a pair of gates here in this SR latch. So as the keyboard is scanned, each row in turn that has a key selected, pressed, will set one of these latches. At the end of the scan, then all of the latches are reset here. The output of this set of latches is what's read by the NASCOM to read the state of this column of the keyboard. Finally, the NASCOM board itself. This one has been modified to add a nice power connector on the side. So when I first acquired this board, it had a number of wire adds on the back side, and I've taken all of those wire adds off and modifications off apart from one. So if we look at the back side, well, firstly you can ignore these red wires, they're just bussing up the power and ground. I'm not sure quite why that was done, but there's no particular reason to take that off. Around here, around the ROM socket, there's some wire adds and a couple of track cuts. So what this modification has done is to modify the ROM sockets. So usually there'd be two 1K devices, and it's been modified to accommodate a single 2K device. Now that's quite a nice mod, and I decided not to remove that mod. It's nice for two reasons. Firstly, the 1K device, the 2708, is a pain to program. And secondly, the 2708 is the only chip on this board that requires a minus 12 volt power rail. So the other thing on the board that requires the plus and minus 12 is the RS-232 interface, which we can quite happily run at 5 volts for modern purposes. So with the ROM modification, we don't really need plus or minus 12 off the power supply at all, which is quite nice. However, we do need the minus 5 volt rail, which is used for the character generator. The character generator chip needs a negative power bias that's generated using the minus 5 volt rail and a Zener diode to generate this negative bias on the character generator. One final thing to check before you power up is that the links are set correctly. There are 3 links that need to be correct. This one is for I/O decoding, which needs to be set to internal. Memory decoding also needs to be set to internal, and the links here control the CPU speed. Can be 1 MHz, 2 MHz or 4 MHz. Board should run at 4 MHz provided you've got a Z80A and a PIO-A. Otherwise you should set it to 2, and if you've got some problems you might want to back it off to 1 while you're debugging. And we need to press reset because there's no power on reset on this board. Well, we've got something happening. You can see that we've got a kind of random-ish display here on the VDU. If I power cycle it, so what's happening here is if I hit reset, then it looks like the processor starts running and doing some really mad stuff. The VDU is software controlled, so to clear the screen requires the processor to be executing code from the monitor. It's not doing that properly. It is doing some kind of stuff, and when we power cycle we do see different sets of characters coming up on the screen. We've got some kind of that chip wasn't properly in. We can see that we've got a stable display. Probably the processor's not running or not running correctly. Something weird's happening, but it's a pretty good start. So let's take a look at the schematics and see what's happening, what might be happening, and where we're going to go next with our debug. Okay, it didn't leap into life, but we got some video out that was stable, so a lot of this circuitry is working. The main clock here is working, the clock dividers, the chain of logic that generates all of the control for the VDU. So that's all of this circuitry here, all of the counters and decode logic here, which is used to sequence the video RAM, and we're clearly reading from the video RAM. We are taking value from the RAM, latching it here. We're loading the data into the character generator. We've got row selects, which are selecting the separate rows of the characters, which are incrementing correctly. We're taking values from the character generator into this shift register. We're shifting out the video data for each line of the display. The video data is combined here with the vertical and horizontal sync pulses, and we're getting sync pulses because we have a stable picture, so everything there is good. We're connecting to a monitor, so we're picking up the video output directly here. This piece of circuitry is the UHF modulator, which would be used if you wanted to connect to the aerial input of a very old television. This modulator never worked particularly well on the NASCOM on a lot of designs. So it's this circuitry here. On a lot of systems, people tended to replace this with a CAN Aztec modulator. Here is our high-tech debug tool for the next step in the process. It's a 2K EEPROM. It's actually in an adapter that allows me to plug it into a 2708 socket, but because this board's been modified, I don't need the adapter, so let's whip the chip out of the adapter and replace the monitor ROM with this test ROM. So here's the test program. You can find it on GitHub. Basically all that's happening is we're writing to 4 incrementing locations in the RAM, and then we do IO port write, which could be used as a trigger, but we don't need to use it as a trigger, and then we read back those 4 locations. So we wrote 00FFAA55, and then we read them back. Depending on which data bus line we're on, we'll see a different data pattern, but in each case, whichever data line we're on, we'll see 2 1s and 2 0s if the RAM's working correctly. Okay, now I've got oscilloscope set up, I've got the test ROM in, and I'm looking at the enable on one of the data bus buffers, and reset it, and I'm not seeing any activity on that buffer at all, and that's telling me that the processor is not executing code, it's not looping, nothing that we expect to be happening is happening. So I'm going to start taking devices off the data bus one at a time to see whether there's a part on the data bus that's causing this problem. Power off first, of course. Here's the connectivity on the data bus. Firstly, we have the CPU, bidirectional 8-bit connection. The 2 ROMs are output only. The PIO, bidirectional, UART, bidirectional, keyboard buffer, unidirectional, output only. And then there's some control signals going to the keyboard, which are driven from the CPU. These are the 2 memory banks. Each of the memory banks is organized in the same way. There are 8 RAMs, each of which has got one connection to one data bus bit and one output bit, and so the 8 outputs go through a buffer 81LS97 to drive onto the data bus. So the same arrangement here for the video RAM. So if we have a problem and the code isn't looping, we can remove all of these devices from the data bus. We can remove the second ROM if there is a second ROM. We can actually remove both of these data bus buffers as well, because we're starting off by testing on the outputs of the RAMs. Once we know that a group of RAMs is working, we can put in its data bus buffer, check that we're getting good values on the output. If we're not getting good values on the output, or putting this part in stops the code from looping, then this part is almost certainly faulty. So having worked our way through each of the RAMs in turn, we can test the 2 buffers. Once we know that these 2 buffers are good, we can put one of these known good buffers into this position, and we can use the other third 81LS97 device back in this socket, and we can test that. And so we can test that all 3 of these parts are good. In order for the NASCOM to work and for us to be able to use it with the keyboard, we need both of these sets of memories to be working. We need the keyboard buffer to be working, but we don't need the PIO or the UART either to be fitted or to be working. So as we start taking parts out to try and home in on a problem, we can leave them out until the board is seeming working, and then we can put them back in and make sure that putting the parts back in doesn't cause a problem. Take out the PIO. Might as well take this out at the same time. The UART. This isn't required for the system to work at the moment. Makes no difference. Let's take out this data bus buffer here. Okay, right, that's better. Now we can see our set of 4 pulses for the 4 reads that we're doing from this memory bank. We've still got a mad display, but now, lots of very mad things happening on the display. There's some flickering on some of the characters, and this is probably due to a faulty, one or more faulty RAM bits in the display memory. The buffer that we removed, IC40, this is the data bus buffer for the keyboard access, and it looks like it was hanging the bus, so it's probably got a faulty output. Right, let's take a look now. We're triggering on these 4 reads. Now we're going to look at the data bus bits one at a time. So this is on the output of the RAM, bit 0 is pin 12. Okay, so we can see here that as we do the 4 reads, we expect to get a 0, 0, 1, 1 pattern, or 2 ones and 2 zeros, depending on which bit we read. We can see we're getting zeros out of each of the bit positions on this RAM. So this RAM is faulty. I'm just going to swap it out right now. I have here that's tested. Okay. Again, we need to hit the reset. And now let's look on the output of this. This part again. And now you can see get a 0, a 1, a 1 and a 0. So this part is working. This is the pattern we expect to see on the 4 reads on the data output pin. So let's go to the next one. Pin 12 here. And again we're getting 0, 1, 0, 1. So 2 ones and 2 zeros as we expect. And this one, oh dear, 0, 0, 1, not quite sure what's happening here. This part also looks faulty. Let's swap this part out. Of course, this is TV. I've already fixed this machine once, and I'll unfixed it so that I can show you the debug process. Now I'm triggering on the buffer enable for the video memory. I've moved the camera a bit so that you can get a better view of the scope. So let's take a look at the data bus bits. and you can see this is thoroughly not behaving. That's totally dead. That one's totally random. And this one finally is one that's behaving correctly. Getting a 0, a 1, a 0, a 1. Okay. Again, this one is working fine. You can see 0, 1, 0, 1. Okay, so I'm going to remove the faulty parts and replace them. Okay, I've now put replacement parts in for all of those RAMs that were not working. Let's try putting in the monitor ROM and see what happens. Okay, here is the monitor ROM. Hey, we have success. We have life. I've got some random junk coming in. That is because the UART isn't fitted, or because the keyboard buffer isn't fitted. So let's put those parts back in. Still going on. Oh, we need to put a new... This part was broken, shorting out the data bus. So we have a new one of those, 81LS97. That's better. The arrow keys are working. Let's enter a small program, see if we can run some code. Load HL with 12FC, increment HL, jump to C83. So, load HL with 12FC, increment HL, and then jump back to the increment instruction. Just single step this program. We've executed the first instruction, and here is a register dump. This is HL 12FC, it's the value we loaded in. If we step again, we'll see it increment, and if we step again, we'll jump back to the increment instruction. So here's our program counter. So now we're back at the increment instruction, so the next time we step we will increment this one more time. So it went to 12FE, jump, increment, jump, increment, jump, increment. Everything looks fine. We can tabulate memory. All looks fine. Okay. Hope you enjoyed that.